Assalamualaikum and hi everyone. I'm Dr. June again. So what's up? So let's continue with the second part of chapter 2. Since in the previous lecture note, the size of the file is quite big. So this time around, I will split this second part of chapter 2 into another two videos, which are part 2-1 and part 2-2, so that it's easier for you to watch it again and again in YouTube. Okay, so let's begin. I will continue our class with the second part of chapter 2, which is mass transfer in a packed bed reactor, PBR. So, in the previous lecture notes, I have taught on mass transfer in single particle. Remember? Where in a single particle, you can evaluate the conditions of the reaction, whether it is mass transfer limited reaction or surface reaction limited reaction based on the value of Kc and Kr. So have look back on the previous lecture note. So you see those part that have you calculate whether Kc is bigger than Kr or Kr is bigger than Kc. Okay, so the same concept will be applied in mass transfer in PBR. In PBR later on, you will see that you also can evaluate whether the reaction in your PBR is mass transfer limited reaction or is limited by surface reaction. A few of industrial reactors are prone to have mass transfer limited because the reactions are carried out at high temperature uh, due to less occurrence of they want less occurrence of side reactions. Okay, so as in our previous lecture note, in mass transfer limited reaction, the surface reaction is so rapid that the rate of mass transfer of reactant from bulk is low and limits the overall rate of reaction. Okay, remember when last time in our previous lecture note, when the reaction is so rapid, the concentration of the reactant A at the catalyst surface, which is CAS, is equals to 0. Okay. So the similar concept that applied in the single particle will be applied in PBR, but consideration of various parameters in the reactor, we need to consider more parameters such as the flow conditions, the velocity, the temperature, viscosity, velocity. You will see that later on. And then also the catalyst weight need to be considered. Okay, so now let's consider reaction in PBR. So we begin by carrying a mole balance on reactant A in the reactor segment between Z and Z plus delta Z, if you can, right? So we consider it is actually from the mole balance is from this part to this part, Z to Z plus delta Z. Okay, we use here W is the same thing. W is the weight of catalyst. All right. So this mole balance you have learned during your reaction 1, if you still remember. Okay, the concept are the same: molar rate in minus molar rate out plus generation equals to accumulation. Okay, so if you look here, the rate, if you later on, okay, you insert all those variable here into the equation. Okay, you will see that end up all these value or the units will be the same, right? Okay, to simplify the equation 11.51, we divided the equation by AC and delta Z. Okay, so here, before I forgot, I want to mention that what is Z. So Z, actually, if you have a look back on the previous slide on the reactor, so we are considering the reactor in Z direction. Okay, so Z plus delta Z. Okay, so here you will see that FA Z W A Z, J A Z, and B A Z is actually considering the direction in the PBR. Okay. So from our previous lecture note, okay, on the single particles, we know that molar flux, which is WA, is equals to JA plus BA, wajaba, okay. However, in PBR, the amount of material transport through diffusion, which is JA, is very small compared to the bulk flow via convection, which is BA. So that's why we can neglect the value of JA here, then we can put it as a 0, okay, because the value of JA is very small compared to BA, okay. Then we can see here also in the equation, U is actually the superficial molar average velocity through the catalyst bed in the PBR. So in the equation, to simplify the equation, we can assume that the velocity of the fluid in the PBR is constant throughout the reactor. Okay, in order for us to simplify equation 1156, okay, so we use the boundary condition like what we have learned in our previous lecture note. So here we use two types of boundary layer, where the first one will be your overall, we can assume that the overall rate of reaction negative RA double prime is equals to WAR, okay. And then the second boundary condition that we can use is that at the external surface of the catalyst, the molar flux is equals to Kc times Ca minus Cas, where the diffusion flux Wa equals to boundary layer is equals to the convective transport across the boundary layer. Okay, so we can see from the equation that direction where when designing the reactor, where the reaction becoming the mass transfer limited reaction, it is not necessary to know the rate law. Okay, and then here you can see that we can neglect the concentration of reactant A at the catalyst surface, because when it is mass transfer limited, we know that the reaction is rapid and the concentration of A at the bulk is much larger than CAS. So then the equation is simplified to minus U dCA dZ minus Kc Ac Ca equals to 0. So then we integrating that equation, and it is becoming equation 1161 as stated in your textbook. Okay. So again, we can see that when you are designing the reactor, the PBR, with mass transfer limitation, we can see that the rate law will not affect the design of the reactor. Okay, from this graph, you can see that how the conversion increase across the reactor length. Again, in order to solve or to design the PBR, for example, if you want to calculate the reactor length, or you wanted to know what is the catalyst rate, or you wanted to know how much the conversion is achieved. So from the equation 1164, okay, you can see that Z just now is becoming L. We need to calculate first the Kc in order for us to solve the design of the reactor. So Kc is, again, is mass transfer coefficient. So I will explain on how to calculate Kc in a PBR in our next part of the video. We have learned how to calculate Kc in a single particle. So more or less it's not that so much different, but we have several methods, so I will explain it in our next video. Okay, so in next video where it will be the last part of this chapter, that I will explain on how to calculate KC, and I'll give you some example of calculation that involve mass transfer limitation to design a reactor. Right, till then, bye.